they can arrange a suitable size for the bus, so a big bus or a small bus. So confirm to BA if you're going to the beach tomorrow, and the bus is included. There's only the fee to get in the beach, and then that's it. And so we are going to listen now to Professor Leandro MALARD from the Universidade Federal de Minas Gerais. So thank you very much.
All right. Okay, now we're fine. Okay, good morning, everyone. So thanks for the introduction, and thanks for the organizers for inviting me here. Okay. All right. So I'm going to show a little bit what we have been doing at the UFMG that's located in Belo Horizonte, okay, in Brazil. So I'm going to focus on the imaging of 2D materials with nonlinear optics, all right? Okay, so what I'm interested in is the light-matter interactions, okay? So I put this picture here from the Pink Floyd album, okay? So basically, what we do in the lab, we have some kind of incident light, can be a laser, can be a white light, can be different light sources. So it goes through the material that we are interested. So something happens, so we have an interaction with this incident light. And for example, here in this case, we have the refracted light from the prism. Okay, so for example, if we measure the refracted light, this angle as a function of the wavelength, so we can know what's the index of refraction of this material. Okay, so basically we do different spectroscopies in order to understand what kind of and how this interaction occurs and get some material properties out of it. Okay, so we can do different things. We can do absorption, photoluminescence, Raman scattering, second harmonic generation, four-wave mixing, and stimulated Raman scattering. Okay, so for today's talk, I'm going to focus on the nonlinear optical properties. So that will be the second harmonic generation, four-wave mixing, and stimulated Raman scattering. Okay, so I don't need to go this into details, but since I'm here, let me say that graphene was the first the 2D material that was isolated. Okay, so we have the graphene sheet. It has very different properties. So we have like a high mobility. It's a transparent membrane, so it's about 2.3% of light absorption. Okay, you have like the Dirac cones, and you also have found use for using as a satellite absorber for ultra-fast lasers and optical modulators and so on. Okay, so after the graphene, so it started to appear new two-dimensional materials. So in this talk, I'm going to focus a lot on the transition metal dichalcogenides. So the semiconducting transition metal dichalcogenides, so the MOS2, MLC2, and different materials. So opposite to graphene, so graphene you have a hexagonal structure. Okay, so these semiconductors here, they have a trigonal structure, and they have 3 atoms in a monolayer. Okay, so for example here, this will be the sulfur or the selenium atoms. You have the metal in the middle, can be the molybdenum or the tungsten. And in the bottom, you have the sulfur or the selenium. Okay. In another 2D material that people are using a lot as a substrate for graphene and for different applications, so you have the hexagonal boron nitride, that you have the same hexagonal structure as graphene, but instead of 2 atom carbon atoms in the unit cell, you have a boron and nitrogen. So while graphene is a zero gap semiconductor, in hexagonal boron nitride is a wide band gap semiconductor. Okay. For the case of MOS2, for example, there are a lot of interest in how is the optical properties of this material. Okay, mainly because it's a real 2D semiconductor. Okay, so before this, people used to study like quant-well semiconductors and all this kind of heat ray structures on 3-5 semiconductors, for example. And now that we have like a real 2D semiconductor, we have a very large exton binding energy. You can have trions, you can have biextons, even in room temperature. Okay, so that's allow us to study this kind of many body effects in more details. Okay, other interesting things about this material is that you have this transition from indirect band gap to a direct band gap semiconductor. When you go down to the monolayer, you can have high on-off ratios and for the FETs and so on. Okay. So now I'm going to introduce just a little bit of nonlinear optics for those that are not familiar with it. So basically, when we apply an electric field to the material, okay, so this material is going to polarize following this equation. So the polarization that you create in the material will depend on the incident electric field, and will depend on this chi1 factor here, okay? But this is just a linear approximation, okay? If you start to increase the amplitude of this electric field, you need to introduce different orders in this equation, okay? So then we have the nonlinear part. So for example, the next order will be like the incident field square. So instead of the chi1, we're going to have a chi2. If you have a stronger field, then you need to consider E over to the third power, okay? And then you have another chi3 value here. So for this part here, this is the second order approximation. This gives rise to different nonlinear optical process. So for example, the most famous one is the second harmonic generation. So in this case, for example, if your electric field has a frequency omega, then you interact with your material. So you have the absorption of 2 photons with energy equal to h bar omega, and then you have a generation of in the second harmonic of this material, so it's going to emit frequency at 2 omega. Okay, so this was discovered in the 60s, just after the invention of the laser. Okay, so this was very important because with the invention of the laser, we have enough power in order to see these nonlinear effects. Okay. So you just here just to show you, you use for example, a laser with the 800 nanometer wavelength. So it interacts with your material, and then you have the emission of the second harmonic at 400 nanometer. Okay, that's twice the energy of the incoming light. Okay. And there are some interesting properties of the second harmonic generation. So basically, the second order polarization that's going to be created in your material due to the incident electric field, you depend on this chi2, okay? And this chi2, in fact, is a tensor, okay? It's a 3×9 matrix, and it depends on the crystal symmetries of your material, okay? For example, if you have inversion symmetry, okay? So it means if your crystal has inversion symmetry, if you apply an electric field, so you change plus here to minus here, so applying an electric field in the opposite direction. If you have inversion symmetry, the polarization should be reversed too, okay? But then if you put this on the on this equation here, then you have minus E times minus E, okay, equals to minus speed. So this is the only way that this can happen if chi2 is equal 0, okay? So it means that for crystals that have inversion symmetry, you cannot have second harmonic generation, okay? And another property is that the intensity of the second harmonic that the crystal will generate, it will depend on how is the incoming polarization of the laser, if it's well aligned with the crystal axis of your material. Okay, if it's okay, of course this depends on this tensor, but for like easy case, I would say so. If you have the incoming laser polarization aligned with the crystal axis, you're going to have like a strong second harmonic emission. But if you misalign your crystal axis with the incoming polarization, so you have a smaller second harmonic amplitude, and if you misalign more, so it decreases. Okay, so you can use second harmonic generation also to probe where are the crystal orientation of your material. Okay, where are the crystallographic axes. Okay. Okay, so now let's move to second harmonic generation in 2D materials. Okay. So the idea of using second harmonic generation to probe 2D materials was to, okay, the first to find if some of the 2D materials generate second harmonic, okay, and if they generate, if you can use second harmonic to probe where are the crystal axes, okay. And one application for that is to build van der Waals heterostructures. Okay, so to build these van der Waals heterostructures, it's important to know what's the alignment between the layers. Okay, the properties of the heterostructure are strongly dependent on this angle. Okay, so if you want to do this, then you, for example, you need to go like to a TEM electron, do some electron microscopy, try to see where's the crystal axis, and then transfer one material on top of each other. Okay, that's not doable, right? It's a very hard experiment to do, and probably you're going to lose your sample in this process. Okay, so we need some tool to determine this crystallographic orientation without difficult sample preparation, without damaging the sample, and it needs to be a technique that it's fast enough. Okay. Okay, so back in 2013, we did this experiment. So we exfoliated MOS2 on a silicon dioxide substrate. This is the AFM image. So here is showing the monolayer MOS2, 2 layers, 3 layers, and 2 layers. Okay, and this is the second harmonic image of this same flake. So here in high intensity is the second harmonic emission of the sample. So we see a very strong second harmonic from the monolayer. In bilayer we don't see any second harmonic. In 3 layer we see some second harmonic with a smaller intensity than the monolayer. And here in the bilayer again there is no second harmonic emission. Okay, and this absence of second harmonic emission can be understood by looking at the symmetries in monolayer and bilayer MOS2. Okay, so in monolayer you don't have inversion symmetry, so it can generate second harmonic. Okay, but in the case of the bilayer MOS2, you have an inversion symmetry in the middle of the 2 layers. Okay, in this case the chi2 is equal 0. Okay, so that's why we don't observe second harmonic generation. So that's one thing. Okay, so only odd number of layers are going to generate second harmonic emission. Okay, and so we did this polarization measurement on this sample. So basically we fixed the input polarization laser at some angle with respect to the sample, and then we rotate the sample. Okay, and then this is the polar plot of the intensity of the second harmonic dependence as a function of this angle phi here, which is the angle between the armchair direction with respect to this with the laser polarization. Okay, and then you have this threefold pattern. Okay, so this is we can calculate because we know what's the crystal symmetries of MOS2. Okay, so we calculate what's the chi2 tensor. Put in that first equation that in the previous equations that I showed about the polarization, induced polarization, okay? And then we can calculate what's the intensity of the second harmonic. So you have this type of equation. So you see that it's a threefold, meaning that the crystal the crystal symmetries they are threefold, okay. And you have this phi naught, okay. This phi naught is the angle between the maximum intensity of the second harmonic with respect to the armchair direction, okay. So basically, we can know where's the armchair direction it's aligned with respect to the input laser polarization. So we can know what's the crystallographic axis of the samples, okay. So we can do something like this. So you have the monolayer emission and the three-layer emission, and then we can directly put what's the crystal orientation of these two flakes, okay. So this was back in 2013. So so last year, or maybe 2 years ago, a lot of different groups start to use this kind of technique to find what's the crystal orientation of different TMDs and start putting them together. Okay, so so we can use, so here's just to summarize this part. So we can know the crystallographic information and orientation of 2D materials, okay. We can also know some about band structure information. I'm not showing here, but we can do like it's what we call a resonant second harmonic generation. So we tune the laser energy and start to probe different extons in these materials, okay. And now another question arises, okay. If we can locate and probe defects on these TMDs by second harmonic generation, okay. Okay, so this work now it's mainly done by Bruno here from Natal, and so for this work we have used MOSE 2 samples, okay. So these are CVD samples, okay, and you see that the CVD samples are quite large, and you have the second harmonic emission. It's very homogeneous. But then you see some dark lines, very straight dark lines around the flake, okay? And what happens is that in 2014 there's this science paper. So they have shown that in this kind of samples, okay, you have this MRC 2 grain in the opposite direction as respect to this other grain around here. Okay, so they are rotated of 180 degrees between each other. Okay, so the second harmonic emission, they have a pi phase difference between the second harmonic dipoles. Okay, so they interfere with each other, and then they create these dark lines, where's the grain boundary on this kind of samples. Okay. Okay, but then we decided to investigate this second harmonic coming from these samples a little bit more. Okay. So in order to characterize what kind of grain boundaries that we have, so this is a TM image. Okay. So in red here, one grain boundary, and in blue, is one grain of your sample, and the blue another grain. They are rotated with 180 degrees between each other. Okay, there's a grain boundary here between the blue region and the red region. Then we zoom in where the grain boundary is located. So we have this image. Okay, so you can see that's 4x4 grain boundary. It's called a twin grain boundary. Okay, it forms when you have this rotation of 180 degrees between the grains. Okay, this grain boundary is not perfectly flat, so we have some other defects also. Okay. Okay, so we really know that there's a grain boundary located in between the grains. Okay, and then what we have done is we put our input laser in the region where there is no grain boundary. Okay, And we detect the second harmonic emission, the far field. Okay, so we are just seeing how is the shape of the light emitted by the sample. Okay, so this is the far field second harmonic emission. So it's just a circular spot. It's have a Gaussian shape because our input laser is also Gaussian. Okay, but when we put the laser between two grains and a grain boundary in the middle, we see this kind of behavior here. Okay, so first you see this dark line just in the middle of the spot. Okay, and this dark line is because of this destructive interference between the two grains. Okay, but you can observe here that you have an emission with angles that are much larger than we would expect if there was no grain boundary here. So you can see the emission of second harmonic coming with a large angle in this case. Okay. All right. So in order to understand this, we did a very simple calculation. We just consider like two dipoles that are separated by a distance d. Okay. So the MOSC2 is in the y plane here. The z direction is the out of plane direction of MOSC2, and then we calculated what's the emitted power over a solid angle. Okay. So theta here is the angle between the z direction and a vector n over here. Okay. And the emission pattern that we have, it looks like this. Okay. So for a small angle here, small theta, you have a destructive interference. But when you start to increase this angle, then you can have a constructive interference. Okay. So this emission here with larger angles, it means that we have some constructive interference in the grain boundaries. Okay. The destructive interference only occurs for small angles. Okay. This is just a 3D plot just to show the same idea. Okay, so for small angles, there is no second harmonic emission coming from the grain boundary, but for large angles, then you have a second harmonic emission. Okay. This calculation we expect like 36 degrees between this and with the maximum intensity of the second harmonic. 36 degrees will be the angle between here and this maximum intensity here. And we found in that experiment around 32 degrees. Okay, so it matches well what we would expect. Okay. Then what we decided to do is do what we call a dark field second harmonic imaging. Okay. So basically, we block this emission that are coming with a small angle and only collect light that are being emitted with a large angle. Okay. So this will be the bright field second harmonic. So you have the bulk emission, and you don't have the grain boundary emission. But when you do the dark field second harmonic, then you start to see the second harmonic coming from the grain boundaries, okay, and also from the edges. Okay, you can see the second harmonic from the edges too. Okay, so basically, with this kind of measurement, we can directly determine what where's the grain boundaries are on the samples. Okay, so here are different examples. So MOSC2, MOS2, and tungsten disulfide. So all of them they show the same pattern. Okay. This sample, for example, there are a lot of grain boundaries and so on. Here you can see a lot of grain boundaries. Let me see if there's, so this is a video. Okay, this is really how the measurement is done. So for example, we can locate the grain boundaries quite quickly. Okay. So here it's about, the frame rate here it's about 0.5 seconds. So it's possible to use this technique to map large area samples and try to characterize the number of grain boundaries and so on. Okay. Yeah, so you see this in the big sample here, you have a lot of grain boundaries. Okay. Okay. Oh, okay, I forgot to mention that all of these results, the samples were in transparent substrate. But even if you use silicon substrate, you can observe the same phenomena. Okay. The only difference that in the silicon substrate, you need to use a high numerical aperture objective. Okay. You need to use a numerical aperture like 0.95 or so. Okay. And then the grain boundaries are very clear by using this high numerical aperture. Okay. The difference here is that because of the silicon substrate, we believe that there are some reflections that are coming from the silicon substrate. So the problem is much more difficult because you need to consider this type of reflection. And then when you use a high numerical aperture, you collect all of this light that are being reflected from the silicon and so on. Then you can observe the grain boundaries. This is even without doing the dark field part. Okay, this is just a bright field. Okay. So now that we can see the grain boundaries, okay, the second harmonic emission from the grain boundaries, we can study it. Okay, so basically what we have done is to measure the second harmonic intensity as the function of the photon energy by using this dark field second harmonic method. Okay, so in red here is shown the second harmonic emission from the book part, where there is no grain boundary, and in green here is where's the second harmonic emission intensity that from the grain boundary. Okay, and for MOSC2, the band gap is about 1.5 eV. Okay, so we don't observe any second harmonic emission from the grain boundaries for energies that are above this band gap. We only observe below the band gap. Okay, and it decreases in a much faster rate than the bulk emission. Okay, so our collaborators from the Penn State, from Vincent Crespi group, so the postdoc Yuan Shi, did these calculations. So he calculated what's the this electron loss spectroscopy. Okay, so he have calculated, considering that the states along the grain boundaries, they are metallic. Okay, so he's considering what's the plasmon resonance of these metallic states. Okay, and what he finds is that for energies that are below 1.5 eV, you start to have some plasmon states. Okay, and the intensity increases with smaller energy. Okay, so this is the plasmon peaks for different momentum transfer between the light and the grain boundary. Okay. One question that can arise is how this momentum transfer occurs. Okay, so the TME image that I have shown, and if you look at the second harmonic, you think that the grain boundary it's a straight line. Okay, so you wouldn't expect that the light couples with this and generate plasmon resonance, but in fact, the grain boundary it's the size of the grain boundaries that they are not very long. Okay, they are a few nanometers long. Then you have a break and another grain boundary rotated with respect to each other. Okay, yeah. Yeah, the grain boundaries, it's metallic. They are metallic. So that was the idea behind it. Okay, because since we observe this enhancement just below the band gap, so we start to think about that this was coming from these metallic states on the grain boundary. Okay, so in fact the grain boundary is acting like a nano antenna. Okay, it's enhancing the second harmonic signal that's being generated. Okay, so now we move to the third order nonlinear optics part. Okay, so if you increase one more order, so we can have an effect that's called the third harmonic generation. Okay, so in this case, the induced polarization in your material is going to depend to the electric field, to the cube power, okay? And then you have then you can understand this as your material is going to absorb 3 photons with an energy omega and going to emit just 1 photon with energy that's 3 times the incoming energy, okay? And for graphene, people have measured this in 2013. And graphene have a very strong third harmonic generation, okay? The chi3 value of graphene, it's quite large, in fact. Another experiment that it's a third order nonlinear optics, it's called 4-wave mixing, okay? It's very similar with the third harmonic, but now we consider that we have 3 different electric fields, each one of it with a different energy, omega 1, omega 2, and omega 3, okay? So if you put these 3 fields on your material, it's going to generate a 4th field, okay? And the frequency of this 4th field, it can be a different combination between these 3 energies of your incoming field, okay? It can be omega 1 plus omega 2 minus omega 3. It could be omega 1 minus omega 2 plus omega 3, and so on, okay? We have a lot of different combinations. So here we just consider this one. So we have absorption of omega 1, omega 2, omega 3, okay? And then your material is going to emit omega 4 energy. And these also have been done in graphene back in 2009. So people have observed the 4-wave mixing signal from graphene. It's also a very strong signal. They change the wavelength and the intensity doesn't change so much. That's because the graphene absorption is almost flat in this energy range, okay? So we decided to do something a little bit different. Okay, we are going to do a 4-wave mixing experiment, okay, but we are going to do this 4-wave mixing experiment close to the resonance with a phonon in the material, okay? So we're going to do what it's called coherent Anti-Stokes Raman, okay? So basically, we're going to put 3 lasers in our sample. 2 of them, they are degenerate. Have an energy equal to omega L. Another laser that have an energy that we're going to call omega S, okay? This omega L is from omega laser. Omega S is called omega Stokes, okay? And we're going to choose the energy between these 2 lasers in a way that omega L minus omega S equals to a vibrational mode in your material, okay? And then we have the 4-wave mixing like this. We have absorption of this one, omega S to this state that's excited vibrational state, and then another omega L, and then the emission of 4th, this wave here that we call omega AS. It's called omega Anti-Stokes, okay? And basically, we choose the energy. Okay, I already said that omega L minus omega S equal to the vibrational energy. And okay, so if you go back to this equation here, okay, so the induced polarization is going to depend on the chi3, okay, and usually when we have something like this, we should divide the chi3 in 2 parts, okay. The first part we're going to call chi3 resonant. This is in a resonance with this vibrational state. The energy difference between this level and here, it matches the vibrational state, okay? And we also have the chi3 non-resonant. That means that we can have a 4-wave mixing that would look like that. It would look like absorption of omega L, another omega L to a higher energy state, then decrease the energy with omega S, and then emit another photon here. But they are not in resonance with this phonon state here, with this vibrational state here. That's what we call non-resonant, okay? And the intensity of the emitted anti-Stokes photon, okay, is going to depend on this chi3 square, okay? So basically, if this resonant part, we can describe this by an imaginary function, and this non-resonant part with a real function, okay? When we take the sum of it and square it, so you're going to have terms that they interfere with each other, okay? Later on, I'm going to show some examples that cases it's good for doing imaging too, okay? So we start by doing this coherent anti-Stokes Raman in boron nitride, okay? So we exfoliated boron nitride samples on the quartz substrate. And here's the four-wave mixing signal as a function of the pump wavelength. So you see that you have some four-wave mixing signal intensity, but when you tune the pump wavelength to around 929, okay, you have an increase on the four-wave mixing signal intensity, okay? If you convert this pump wavelength to the Raman shift, that will be the energy difference between the two lasers, okay? So you see that the resonance occurs around 1360 wave numbers, okay? If you do a normal Raman, this corresponds to this Raman band of boron nitride. That's the vibration of the boron and nitrogen, just one against each other, okay? And then we do it the same kind of experiment in graphene, okay? And graphene, what happens is that you have very strong four-wave mixing, but then when we tune the laser, the difference of the laser energies to the Raman peak of graphene, that's the G band, okay? Instead of observing enhancement of the signal, you just observe a decrease of the signal, okay? So basically, in order to understand this, we need to take a look at the band structure of the two different materials. And in graphene, so because it's a zero band gap semiconductor, okay, all of these four-wave mixing, they are resonant, okay? So you have the electronic resonance, you have the resonance of the incoming photons with the electron states, and also we have the resonance with the phonon states, okay? In the case of boron nitride, because it's a wide band gap semiconductor, it's an insulator, right? So you don't have the resonant part related with the electronic part. You just have a resonance with the phonon, okay? And basically, there's a simple theory that's called a funnel resonance that was developed in the 70s, okay, that addressed the following problem. If you have the electronic continuum states and you have a discrete, in our case, it's a phonon state, okay, in this electronic continuum. So in order to compute how this chi3, how is the resonant and non-resonant part, okay, this will depend on how strong is the electronic continuum contribution for this chi3 and how strong is the phonon contribution for this chi3, okay? So there's a phenomenological theory in order to describe this. This was developed by Ugo Fano back in the 70s, okay? So you can have interference between these two states, okay? And Fano proposed that you have an equation that's it looks like this, okay? So here's the phonon energy, okay? Gamma here is the phonon lifetime, okay? And also you have this Q parameter here. So basically it's if Q is much smaller than 1, then you have this electronic continuum is going to be the most strong contribution. If this discrete state dominates the response, so this state is going to contribute more, okay? Then Q is much larger than 1. So we use this kind of equation to fit our data, and you can see that the Q value for graphene is smaller than 1, and the Q value for boron nitride it's much larger than 1, okay? So it makes sense, right? In graphene, you have a very strong contribution from the continuum electronic states that are available, but in the case of boron nitride, you don't have this contribution from the continuum states. You just have the contribution coming from the discrete phonon states. Okay. We have also characterized the chi3 for graphene and for boron nitride. So chi3 here it's around 9 to 10 to 6. This is a picometer cube over volt square. Okay. And for HBN, it's 1 order of magnitude smaller. Okay, it's much smaller. Okay, so following this work, so we started studying four-wave mixing, second harmonic generation in the TMDs materials. Okay, in this case now we are going to be in resonance with the extone states. We are not going to be in resonance with the phonon states anymore. Okay, so these are some preliminary data that this my student it's working on this. So here's the MOS2. So the black dots here is the absorption of MOS2. So here we have the first absorption, that's the A extone, and another absorption peak here, that's the B extone, okay, of MOS2. In blue here is the second harmonic emission, okay. So the second harmonic, in this case, what we do is we have 2 photons, okay. So we put the energy of the laser close to the half of the energy of the A or the B extone, okay, and then you generate second harmonic that it's in resonance with the A or the B extone on MOS2, okay. Then you also observe following the absorption, you see that the second harmonic, you have a strong enhancement close to the A extone and another enhancement close to the B extone. And for the four-wave mixing signal, what we do is we have the 2 lasers, okay. So we have the first lasers, the 2 absorption of this one goes to some state with a higher energy than the A and B extone, and then the other lasers excite the extons in resonance with the A and B extone, and the emitted four-wave mixing is going to have the energy of the A or the B extone. Okay, so this is the four-wave mixing signal as a function of laser energy is these red dots. So for the A extone, you see a strong enhancement, but for the B extone, you just don't see anything. Okay, we see something, but we are not even sure that the B extone, he's repeating all these measurements. So here, I'm not going to show here. This is some ongoing work, but we have measured the other different transition metal dark ecogenides, and the trend it's very similar. Okay, we don't have the four-wave mixing emission from the B extone. Okay, so this is a result that we don't understand up to now. We would expect that the four-wave mixing, since it's a third nonlinear process, the selection rules should be very similar to the linear optical part, okay, but so we still try to understand how the reason for that, okay. Now I'm going to enter that what people are calling now like vibrational microscopy, okay. So basically we're going to make use of this idea of using the third order nonlinear optics, the four-wave mixing, that is in resonance with some vibrational state in your material, okay? So the idea behind is that we're going to combine the Raman chemical specificity with the high signal throughput of nonlinear optics, okay? We want to do some fast imaging in our samples that have some chemical sensitivity, okay? So the basic idea, I'm not going to be in details, but if someone wants to know more about this, we can discuss. So for example, when we do Raman spectroscopy, we shine a laser with energy omega-1 in our sample that have some vibrational mode omega-9, omega-ni, okay? And because we are doing Raman, so usually the laser energies are much larger than the vibrational frequency of your material, okay? So imagine that you have like harmonic oscillator in your sample that's vibrating with a frequency omega ni, okay? And then you try to force this vibration with an electric field that is oscillated at omega 1. If omega, sorry, here I make some confusion, omega L, for example. If omega L is much larger than omega ni, so basically I'm trying to push the oscillator that is completely out of resonance, okay? So the resonance peak is going to be in omega ni, but I'm trying to force the oscillator in a frequency that it's in a completely different, okay? But then if I put two lasers on my sample in a such way that the second laser, omega 2, has a energy that's omega 1 minus the vibrational frequency of your material, okay? So when these two lasers go into your sample, it's going to create a beating frequency, okay, that have exactly the frequency of your oscillator in your material, okay? So basically, this beating frequency is in resonance with the vibrational frequency. So we are going to like do a coherent vibrational states on your material, okay? So basically the Raman intensity is going to be amplified, okay? So there are different techniques that can be used in order to see this effect. One of it is the coherent anti-Stokes Raman, okay, that I have already shown some results on graphene and boron nitride. So basically on coherent anti-Stokes Raman, I have two pump laser, omega S and omega P, okay, omega S and omega P, in order that the energy difference between them frequency omega, which is the frequency between some normal mode in your sample, vibrational normal mode, okay? And then you're going to observe an emission of the car signal, which is the four-wave mixing signal that is in resonance with the phonon state, okay? And then you can detect this light, and you're going to measure this car's process. There are some problems of doing that with microscopy. I'm not going to be in details. Mainly because cars, as I told you, there's the chi-tree is always you have the resonant part and the non-resonant part, okay? So sometimes depending on the type of samples that you have, for example, in graphene, for example, okay, the electronic contribution was so large that the phonon part was very small, okay? So for doing cars microscopy on graphene would be not ideal, okay? But we can do something different. That's called the stimulated Raman gain or loss, okay? So when the two lasers go into the sample, there is an energy transfer that's mediated by this vibrational mode. So the pump laser can lose some intensity. It can lose photons. And the omega S laser can gain some photons, okay? So basically there's an amplitude change on your input laser, both on omega P and omega S, okay? The problem is how we detect this, because we are pumping the laser, the sample with this laser, and we want to detect some amplitude difference, which is very small. So the laser noise usually is much larger than the expected intensity difference here, okay? So what we do is we modulate one of the laser beams. In the case, we modulate the Stokes beam with a high frequency modulator. Okay, so it's about 10 megahertz. It goes to the sample, and then we block this laser after it goes to the sample, and only detect the pump beam. And then we detect the pump beam with a photodiode that it's connected to a locking amplifier. That it only reads the frequency of 10 megahertz. Okay, it means that when there is some vibrational mode in your sample that matches the energy difference between this laser and this one, there is some energy transfer that is going to be from this laser to this one, and it's modulated at 10 megahertz. Okay, and then I can detect this with a locking amplifier. Okay, so that's the full system here. So you just have a laser with the two beams. We separate, then modulate one of them. Goes to the sample. Here's a mouse. Okay, I'm going to show why it's a mouse. And so we detect the transmitted signal, block one of the beams, and then we measure the photodiode and the locking amplifier. Okay. So this is just to show that the system works. These are 3-micron polystyrene beads. Okay. So this is a 150 micron image. Okay. The laser is tuned to this vibrational frequency here and 3055 wave numbers. That's a Raman mode of the polystyrene. Okay. And the whole image takes 700 milliseconds. Okay. If you're going to do some Raman image with such a large area, you're going to take hours, okay, more than 6 hours at least. Okay. So it's a very powerful microscopy method. Okay. So right now we are using this to study boron nitride. So the student Renan, now he's exfoliating the samples on quartz. So here's a simulated Raman imaging of the boron nitride tuned at this frequency here. So these are very thick boron nitride. Okay. These are some other flakes that have smaller number of samples. The image quality here is a little bit hard to see. So this is the optical image, this is the SRS image. Okay, so there are some thin flakes here. So in the SRS, in the computer at least, we can see it. Okay. So here's a thinner flake. So there's, in the optical image there, you can see this shadow here. There's some thin HBN flake, and here's the SRS signal from it. So the idea is to try to use SRS in order to count the number of HBN layers. Okay, so this work is still in progress. We found out that it's very hard to find a single layer of HBN. At least we didn't find up to now. Okay. All right. Another kind of completely out of the 2D material field is to apply this same technique for studying biological systems. Okay. So here I'm showing that this mouse brain tissue. Okay. So this mouse, it has Alzheimer's disease. Okay. It's a model that we use. So that's the brain tissue. Okay. And then we do SRS in this frequency, okay, and then we start to see some accumulation here, and here, some bright spots here, okay. And basically, when you have the Alzheimer's disease, okay, you have these amyloid plaques that start to form in the brain, okay. People don't know exactly the relation of the amyloid with Alzheimer, but there's a clear connection between them. Okay. So basically, we can locate these amyloid plaques. So you have one here, another one here, another one here. So after that, after the image, we stain the tissue with curcumin and do fluorescence. Curcumin likes to attach to the amyloid plaques, and then we can just see, okay, this is really amyloid plaque here. There was another one here and here. Okay. So the whole idea of using stimulated Raman scattering imaging biology is to get rid of the fluorescence staining. Okay. So if you want to have some biomedical application in the future, it's desirable that you don't use any fluorescent probe in your body, right? So that's the case. Here's a more nicer image. So here the brain tissue again. So now we can see clear the amyloid plaque here. That's a zoom, the amyloid plaque with a higher magnification objective. Okay, so we can see clear the amyloid plaque by the stimulated Raman image. Okay, I just want to make some advertisement just before I finish. So So FMG, it's in Belo Horizonte, okay, so we have this, it's a big campus, okay, so the physics department, it's around here. So here's the Pampulha Lake, it's a very nice area, okay. Here's the football stadium Mineirão, okay, when this was, when happened Mineiraço, okay, when Brazil lost to 7-1 to Germany. So that's it. It became famous about that, right? So our post-graduation program, it has the highest score in CAPES. Okay, so we have some opening position for PhD, that's each semester, right? And right now there are some postdoc openings. That's we have 3. I think it's going to be 3 positions. So, okay, it happened that 2 weeks ago, CAPES said that you would block these fellowships, and looks like now they're going to release some of it. So hopefully in the next weeks we're going to open these 3 positions. Okay, and so the students, they organize this workshop. So that's in the 3rd edition. So it's very nice because the student can do their own organization of this workshop, and they discuss a lot of physics and their results. Okay, and another thing that I would like to call attention is that we have 2 companies. One is called City Nano. Okay, so City Nano basically it's doing a lot of carbon nanotubes and other 2D materials. Okay, MOS2 and graphene, and there is also the MG Grapheno. Okay, which is another company that's related with there are some investment from the state in order to do graphene synthesis in large scales. Okay. Okay, so just back to the summary. So we have shown that second harmonic can be used to characterize 2D materials, okay, the crystallograph directions, the layer stacking order, okay, and also now the grain boundaries. So for the 3rd order nonlinear optics, we have observed the coherent Anti-Stokes Raman in graphene and boron nitride. So the line shape of it was understood in terms of these different contributions from the electronic continuum and phonon states. And right now we are very interested in this vibrational microscopy, okay. We think there are a lot of opportunities both on 2D materials and for biological applications, okay. So I'm very happy to collaborate with someone that has some idea that we can use this kind of technique. Okay, so thank you very much.
Time for a few questions.